Hello everyone, welcome to my video. In this video, we are starting the last chapter of this course, Plane Kinetics of Rigid Bodies. We will only cover up to section 6.6, by the way. We have come a long way making it to chapter 6. I'm putting the two keywords kinematics and kinetics here again to give you the reminder. For chapter 4, we did not address anything in class. There is a video covering section 4.1, 4.2, and 4.3, as well as there is a video with examples of how to do some basic analysis for systems of particles at kinetics level. The example video is unlisted. You can find the link on Learn. Here in chapter 6, we will be pretty much using everything we have learned from this course to solve kinetics questions for rigid bodies. Some equations from chapter 4 will be modified here to make it suitable for use on rigid bodies. I will make sure explaining all equations we're going to use, so you're clear about it. A quick debrief of chapter 4, the plane motion contains a mass center G. All forces on the body are projected onto the plane motion 2D. That's what we are only interested in. Three general basic equations, sum of Fx, sum of Fy, sum of moment about the mass center G. By now, you should be able to isolate the body or system, clearly identify the boundary, and draw a free body diagram thoroughly without missing any forces. Without these basic skills, this chapter will be a lot harder to follow along, so I hope you already mastered those skills. Similar to what we did in section 5.7, I will try to focus on showing you how to use the equations instead of diving too deep into how they were derived. There are two basic equations that governs all motions, with G representing the mass center. Number one is sum of F equals to mag. This is the resultant force acting on the body equals to ma with respect to mass center. The other one is sum of mg, the moment about the mass center G equals to hg dot. This means the resultant moment about the mass center equals to the time rate change of angular momentum. Okay, keep these two equations in mind because these are the two basic governing equations will be used throughout this entire chapter 6 or until section 6.6 that we were covering. From these two equations, we actually have more ways to present a free body diagram other than the way we are used to. On the left is the conventional free body diagram that we are familiar with, where you draw all forces of the body. Then in the middle, we have the diagram called equivalent force couple system diagram. I want to look how this diagram is related to the free body diagram on the left. This is essentially presenting all forces as a single resultant force with a resultant moment about G. Okay, these are still forces, but just in a nicely resultant way. On the very right, we have the kinetic diagram. Comparing this one with either the free body diagram or the equivalent force couple system diagram on the left, the kinetic diagram on the right, as its name suggests, tells us how this object moves as it gives us the acceleration and change of angular momentum. If I have to tell you that you must know how to use one extra diagram other than the free body diagram, that would be the kinetic diagram on the right. If you look at it again, this is essentially the right-hand side of the governing equations. Well, on the left-hand side is sum of F and sum of mg, which gives you a free body diagram or the equivalent force couple system. And on the right is the mag and hg dot, the time rate of change of angular momentum. Okay, left-hand side is force, right-hand side is kinetics. Here we focus on these two equations again, sum of F equals to ma, Newton's second law, which I hope it does not need more explanation from me at this point. For the sum of moment equation, sum of mg equals to I alpha, where I is a mass moment of inertia of the body and alpha is the angular acceleration of the body. think of the moment of inertia I as the rotational analogy of mass. Just like mass resists linear acceleration, moment of inertia I resists angular acceleration. Right? Just the nature of the body of the object does not want to move. So if you apply a torque or rotational force to an object, its angular acceleration alpha will depend on how large the moment of inertia I is, just like F equals to ma for linear motion. Right? Think about this. Let's say this is a very heavy item in my hand. The mass is large, so the inertia is large. When I want to push it, I need to exert a very large force to be able to let it go. For the moment of inertia resist angular acceleration, the same thing. Instead of linear pushing, I'm trying to rotate. Like imagine this is very heavy. Now this is not very heavy, so I can rotate it easily. But if this object in my hand is very heavy, I have to exert a very large moment to rotate it. Okay, so linear motion and rotational motion, they are very similar. So think about the moment of inertia. It's just something resists to move. That's representing the nature of the object. Here's a brief review of most common scenarios you will encounter in this course. The mass moment of inertia, or I. For detailed reviews, please refer to Appendix B in your textbook. The generic equation can be used for any scenario is this I equals to integral of r squared dm. This generic equation can be applied for any shape, such as triangulars, plate rotating about one vertex, like any kind of rotation, any kind of shape. This kind of situation is not common, so we have to use this generic equation, integral of r squared dm, to calculate from scratch for I. I just said uncommon. That means there are some common scenarios which allow us to use somewhat simplified version of this equation. First one you see here is called point mass approximation. This is I equals to r squared m. Can be used when the object can be treated as a point with mass m that is rotating from an axis with distance r. One example is the ball tied to a string swing as a circle. Okay, so that ball can be treated as a single point with mass. The other common scenario is called the radius of gyration, I equals to k squared m. This is based on an assumption that the mass of the object can be treated as if it is essentially concentrated at one point, that is in distance k from the rotating axis. It's very similar to the point mass approximation. Okay, one is r squared, one is k squared. And where this k is called the radius of gyration. And in questions, you'll be seeing that the radius of gyration is given, then you know you'll be using the I equals to k squared times m to calculate the I. For some of you, those two equations might be new, so please make sure you take detailed notes. As for when to use them in questions, I just said, you can expect to see clear wording indicate where you can use them, either use point mass approximation or given the radius of gyration. There are common shapes, rotates in common ways that people know them very well. So this type of table is available to you to read. Please learn how to read this table. Okay, for example here, looking at the thin circular disk, if it rotates with respect to x-axis or y-axis, the mass moment of inertia, I, can be calculated using 1/4 mr squared. That is when your disk is rotating with x-axis or this y-axis. If it rotates with respect to the z-axis here, then I is calculated as 1/2 mr squared. And another common axis this disk may be rotating about is with respect to this z prime axis. If that's the case, then your I is calculated as 3 over 2 mr squared. Okay, so these three different equations are really depending on which axis, how this thin circular disk is rotating. Think about how easy it is to rotate something. For example, if my rotational axis is in the middle, it's very easy to rotate, right? Very easy to rotate. If my rotational axis is here at the end, right? Especially when the mass is large, it's getting harder to rotate versus my axis in the middle. So it's really depending on where your axis is, how this object is rotating. The full table is available in your textbook, table D/4. This table will be provided to you in the exam if needed, so you can save the space on your formula sheet. Do not draw this. But please make sure you know how to read this table. Back to these two general equations. With some manipulation, the sum of moment equation can have three other alternative formats that sometimes can be more useful than the original one, depending on the situation you're dealing with. Equation 1 and 2 are similar, as one is in scalar form and the other one is in vector form. They can be useful when you are interested in a particular point of the body. Oftentimes, this point can be chosen anywhere based on your preference, such as in this example here on the right. If we choose point P as the intersection of F1 and F3, then F1 and F3 do not have moment about point P. The only force that make a moment about P is F2 in this case. So if you choose P as your reference point, instead of just the mass center G, when you're calculating the moment, the only force will create a moment is F2. Then you can see in the kinetic diagram on the right, the only two things left are ma, which is caused by F2, and I alpha, which is caused by the angular acceleration of the object itself, if there is any, if it's rotating. Lastly, in equation number 3, when the particular point P is chosen to be at the mass center G, then we will call that point as O instead of P, right? But remember, either O or P, this is essentially just a point that we are interested in. If you want, you can call them any letter. In the third equation, as an example, we are interested in the mass center. So if all forces are pointing towards the mass center, then the moment equation reduces to simply only contain the self-rotation part. And there's no moment is being caused by any external forces, just the rotation itself. Lastly, we have the system of interconnected bodies. As you can see, the equation can be used for interconnected bodies are very similar to what we already know. The only heads up here I would like to give is, since there are two bodies, and make sure you clearly identify which force is on which body, because each body will most likely have different mass. Sometimes they have same mass, but most likely they are not. That means when you're calculating the MA part, the M is different. So make sure you clearly see which body has which force, or what force is acting on which body. While dealing with the moments, remember to consider all objects and all forces that are at present. Now comes to give you some tips on how to start solving a question. I'm breaking this into three categories: kinematics, diagrams, and equations of motion. After reading the question, you should be clear about how does this object move. Then, with the help of the free body diagram, you should be able to see why does it move, and then apply equations, either sum of forces or sum of moment. Back to the category 1, the kinematics, there are situations where relative velocity or acceleration need to be considered. You will need to use this knowledge you obtained from previous chapters, relative motion. For diagrams, other than the free body diagram, the kinetic diagram, remember the right-hand side, the MA and H dot, the time rate of change of angular moment. The kinetic diagram can be very helpful in terms of understanding what is the root cause of certain movements, why it moves this way, why it rotates. Lastly, when setting up equations, clearly identify the knowns and unknowns. You will see a lot of variables, a lot of values, numbers, right? Which one is something you want, which is some information it is going to help you to set up the equation. And there might also be some non-essential distracting information. In pure translational motions, the basic equations sum of F and sum of m can be reduced or simplified. The acceleration of mass center g is same everywhere on the body for translational motion. Since there is no rotation, alpha in the momentum equation is 0, which means the sum of momentum is 0. But if you choose a point P instead of using the mass center g, the sum of moments will be calculated as MAD, the sum of MP. Just make sure if you're either using a particular point P or you're using the mass center G, really depending on your choice. Speaking of choice of point P, the choice is yours, and it really matters. This can reduce lots of heavy calculation to save tons of time and energy. Also, choosing the right coordinate system matters. XY system versus the NT system. Right? Less likely we're going to use any polar system. So XY or NT, that's the two most common ones. Looking at the right-hand side here, the same for three forces applying on the object. Due to the different path, using the NT system would be probably more, I would say, more straightforward and easier to solve because it's on a curve. Here's a list of recommended readings. Thanks for watching. I'll see you next time.